Hi everyone, I'm Robert. I'm a PhD student, second year PhD student at Caltech, working in Professor Anima in the Commerce Lab. I work a lot on like AI for science and AI for math. And this poster is about actually Tensor-GaLore, which is kind of an extension of GaLore. So in GaLore, the original work was that we wanted to reduce optimizer memory state. And so the goal over there was to kind of, instead of like LoRa, which decomposes the weights into like a low rank decomposition, we project the gradients onto a low rank subspace. And that only usually worked on like matrices actually. So we are looking at actually in the case of Fourier neural operators, which are kind of these extension of neural networks to learn like function spaces and try to learn the solution of PDEs. And the weights in actually neural operators, at least FNOs, are actually tensor-based weights. And we cannot use color on tensors without kind of like reshaping it into a matrix, because the point over there is that if you do that, you actually kind of lose the structure of the tensors and the multidimensional relationships, as well as that each dimension kind of has its own kind of information. So what we propose is to use actually directly decompose the tensor weights, the tensor gradients actually into the low rank subspace using Tucker decomposition. So Tucker decomposition basically is like a higher order extension of SVD, where you decompose the gradients onto these orthogonal factor matrices and this core tensor matrix, and you project the gradients onto these using these factor matrices and update the Adam optimizer states or any kind of optimizer you use, and you would project the gradient back when you're trying to update and do the backward pass. And we see the main results on different like kind of PD data sets, the fact that we get much better generalization, which is very different compared to like the original GaLore paper, where you had like same convergence, the same perplexity. And we also see that we reduce optimizer memory state up to like 76%. We have done large scale experiments on the highest, like say 1024 by 1024 resolution on Navier-Stokes, which is really, really hard to do. And this is one of the few works which we can kind of scale up these FNOs into a large model. In a follow-up work, we also prove like theory of this why it converges, and like we show that FNOs actually, the weight matrices will, or the gradients in particular, will go into like this low rank subspace. And we hope that this can be used when you're trying to scale up neural operators for like large scale PD solving, like climate forecasting and such like that. So thank you everyone. Yeah.